While it is possible and useful to think of light in some cases as a wave, it is also necessary in other situations to think of light as a particle. So we talked before, that means last year, about the photoelectric effect. And the photoelectric effect only can be explained by assuming that electromagnetic radiation is transferred in particles. So what that means is that there are particles of light which are called photons. You can calculate the energy of a particular photon by using Planck's constant, and it's a direct relationship between the frequency and photon derived or connected by Planck's constant. You will, in your study of science, many times hear people refer to the wave-particle duality of light. And what this is referring to is that depending on the experiment that you're looking at, sometimes it's more convenient to think of light as a wave, and other times it's more convenient to think of light as a particle. So just a couple of definitions. We have the continuous spectrum, which is kind of like what we see with the rainbow, and we have a line spectrum, which is what we see with the gas discharge tubes, which we've looked at. So let me just go forward a little bit here. Okay, so the idea of the Bohr model is that the electron and hydrogen moved around the nucleus in only particular distances from the nucleus. And the great thing about Bohr's model was it enabled people to calculate from theory what these wavelengths should be. So there was good correspondence between theory and experimental information, experimental results with hydrogen. So the idea here was that there were different levels, 1, 2, 3, 4, 5. The visible spectrum results from transitions to the second level. This is called the Balmer series. So you have a 5 to 4, you can have I'm sorry, not a 5 to 4, 5 to 2, 4 to 2, and a 3 to 2. So that's the Balmer series. And as you have less energy transferred, then the wavelength of the light becomes longer. So that's the reason this one is red, and this one's green, and this one is blue. This is another way really of just looking at the same thing. So these are the different transitions that are possible. In this case, all of these are for the transition to the second level. So the equation that Bohr derived, which you can go about finding this wavelength or this energy a couple of different ways. But anyway, in this particular form, if you know the number, the energy level, so that would be the final minus the initial energy level squared, and then this constant, which is called the Rydberg constant, then you can calculate the energy, and once you calculate the energy, you can kind of work backwards and calculate the frequency and then the wavelength of light. Well, the Bohr model was very successful for hydrogen, less successful for helium, and then it really just started to fall apart. So it was clear that while there was some part of it that was right, there was more going on than was understood at the time. And the result of this is that scientists search for a way to describe, or better describe, multi-electron atoms. So you could go through and calculate. I'm not going to do it. Well, I guess we did do it already. So 3 to 2, that was the longer wavelength. So that was the red line, and I think 4 to 2 was green, and I think 5 to 2 was blue.